on the second day of DBT sponsored 2 days webinar and virtual visit of TIFR labs. I, on the behalf of PG Department of Physics, Kanya Mahavidyalaya Jalandhar, welcome our honorable invited speaker, Dr. Professor Venugopala Janta from Tata Institute of Fundamental Research, Mumbai. Our esteemed faculty members and all our dear students. Yesterday, Professor Dr. Venugopal explained and elaborated theoretical concepts of spectroscopic techniques. Starting from the types of sources used to excite samples, he went through different measurement techniques, which included differential reflection and differential transmission. During his talk, he elaborated the concept of excitons, quantum nanostructures, photoluminescence, etc. So your diagrammatic description and the way of explaining concepts grabbed the attention of audience. Today's students as well as our faculty members are very excited to have the virtual visit to labs of your esteemed channel. So without any further delay, I request Dr. Venugopal to take over the charge, sir. Please.
Thank you, ma'am. So what you're seeing is our messy lab. So I guess, like as people say, if you're working, like you tend to keep your surroundings dirty. If everything is clean, like maybe nothing is being worked. So this is how an optics lab, typical spectroscopy lab looks like, with lots of optical components. So our main workhorse, as I said, we'll start with the sources. So we use this so-called tsunami. Tsunami is a 80 femtosecond pulses. The pulse width is 80 into 10 power minus 15 seconds. So each pulse width is, and 80 million pulses come per second. So each pulse will have millions of photons in them. Okay. So from there, like we go down to one single photon per pulse limit and then do our measurements. Okay. So this is a tunable laser where we can tune from 700 nanometer to 1000 nanometer wavelength. Okay. So we can use this to excite different molecules, different semiconductors or quantum structures. Okay. So this other one which you see here, the black one here, so that's a helium cadmium laser. So this is a titanium sapphire laser. So that titanium doped sapphire crystal, so is used to pump this laser. So there is a ND laser, like so neodymium doped laser, like so, which, I mean, there's a crystal inside which is pumped by a diode laser at around 1064 nanometer. So that's all integrated inside the power supply here, which is below, right? And then this generates green light. So the green light is used to pump the titanium sapphire laser crystal, which is inside. So that emits the green pumped titanium sapphire crystal emits red to near infrared wavelengths. So 700 nanometer to 1000 nanometer wavelength can be, output of this laser. So this is a broadband, like so as I said, delta nu and delta t are inversely proportional through the uncertainty principle. So if we have 80 femtosecond pulse, so that means the spectrum of the, because in time, delta t is very, very small. So the spectrum delta nu will have spectral width will be very, very broad. So for 80 nanometer pulse width, we typically get around 12 to 15 nanometer of spectral width. Okay, so the delta lambda is around 12 to 15 nanometers. On the other hand, you see here the black one which I showed you is a helium cadmium laser. So helium cadmium laser is a gas laser. You see, like the size of it, like you see this one, it's much longer compared to the small one. You can see the comparison between the two. Okay, so this one is a short pulse laser, and it's a broadband short pulse laser, and this is a gas laser. Okay, helium cadmium laser, so which gives you single lines. So they emit two different wavelengths. So 442 nanometer and 325 nanometer, two different wavelengths are possible as output of this black color laser. Right. So because these are atomic transitions in gas molecules, So the line width is very narrow. So we can use it for example, fluorescence excitation studies and things like that. So it's a continuous wave laser. So there are no pulses emitted by this. The photons are continuously uniform number of photons come out in time. Unlike this one, it comes as a pulses. 80 million pulses come per second using this tsunami laser. So you also have this small laser here, the yellow one here. So that's a helium neon laser. So that's also a gas laser. It emits 632.8 nanometers. Just to tell you that the line width, okay, compared to 15 nanometer, which you get here, the line width or the spectral width of that laser, okay, or even for that matter, like helium cadmium laser is typically of the order of like 0.1, 0.2 nanometer kind of spectral width. So they are very narrow line widths which are possible from the gas lasers, which emit between two particular transitions in the atomic spectrum. Right. So as I said, like, so these are expensive sources. So if you want a broadband source, so for example, you can use a simple halogen lamp. Okay. So this is a 5 rupee laser. Like, so if you see our room light, the problem with it is like the light is coming out in all directions. But if you look at the laser output, it comes like a pencil beam, right? It's a beam of light comes out, right? Lasers we have seen, all of us have seen laser pointers. So the laser light comes out in a straight line with little divergence compared to the normal light. So if you use a halogen lamp, right? So the light is going emitted in all directions, but we want a beam of light. To generate that, we use a combination of pinholes. So these are small holes which we use, and then we use this combination of lenses to collimate the beam. I'm not sure if you can see this. It's very weak, which is seen on the spot which is seen here. See the spot here, like, so that's the light spot. So this mirror is sending it to this mirror, and then it's coming to this lens, and the lens is focusing onto the sample which is inside this blue color thing, which is a cryostat. Okay, I'll come to that later. So the light beam is basically combination of pinholes, lenses, and mirrors are used to send the light beam onto the sample. Now the sample either reflects or transmits, right? So we can measure the reflected light or transmitted light, and we can see what the spectrum is coming out of this. Right? So for example, there is a sample inside this, which is a MOS2, molybdenum disulfide, which is a 2D material. So it's on a sapphire substrate. So sapphire, because like it transmits all wavelengths or most wavelengths in the visible to near infrared. So we use that as a substrate. And then the transmitted light or the reflected light can be picked up by a fiber here. So there is a lens in front of the fiber, and this black thing here is the fiber, which is sent all the way up. It's coming here and then going into the spectrometer. So this is a fiber coupled spectrometer because the fiber is picking up light from the transmitted path of the sample to the spectrometer. So this spectrometer, this box, as I said, has to measure a broadband spectrum, so we can use it. So for example, I can measure the spectrum from 500 to 1000 nanometers, right? And then the grating will move in steps and then acquire different spectrum. So it's taken from 400 to, so here 550 to 700, 700 to 875, and then it adds all of them together. Right? So this is a spectrum which we are seeing. So as I discussed yesterday, we see that there is something, some dip here in the spectrum. So this could be related to the absorption in the sample, right? So I'm just giving it as an example that, so by measuring the spectrum which is falling before the sample, okay, and after the sample, so we can measure the transmission. In the same way, like we keep the fiber, position the fiber here in the reflection, we can measure the reflected spectrum. So we can get the reflection as well as the transmission spectrum. We know that like R is the reflectance, and T, capital T, R plus T plus A is equal to 1. Right? Reflected light, transmitted light, and absorbed light, the sum of all three should be equal to the incident light. So 1 is equal to R plus T plus A. So if you measure R plus T, so we can find out the absorption spectrum from 1 minus R plus T. Okay? So we can measure the reflection and transmission in a simple setup. This hardly costs few thousand rupees to set up this kind of setup. But there are also commercial setups where you can spend like say 20 lakhs or 30 lakhs to buy a commercial setup. Nowadays, so this is one spectrometer which I showed you. This is called a half-meter spectrometer, but you can also get spectrometers nowadays of this size. So these are fiber spectrometer. It's a fiber-based spectrometer. So these are much cheaper, and just look at the size. So the difference between these two, the small one and the big one, is the resolution. So how precisely you can find the wavelength of the light which is incident on it, and how can you resolve two different colors or two different wavelengths which are falling on the spectrometer. Okay. So a half-meter one, it gives us a resolution of 0.1 nanometer. Right? It can go even smaller depending on the grating which we use. But in this spectrum which I'm showing, so 500 nanometer to 1000 nanometer, we measure the spectrum in a few seconds time. And the main point is the resolution is about 0.1 nanometer. But if you use the small one for the same range, okay, the small spectrometer, the resolution will be about 1 nanometer. So it's 10 times poor resolution. Okay? But for some applications, it's good enough. You can use them. Okay? So these are different kinds of sources. So there's one more source which I'll tell you. So this is called a super continuum source. Okay? So the beauty of it is there is inside this, there is a laser, okay? A small laser which is pumping a small piece of 1 centimeter long fiber. Okay? So the fiber has nonlinear optical properties. I briefly discussed like where the nonlinearity coming from. If my pump intensity is very high and the nonlinearity, the chi2 is large, then I can generate some frequency, difference frequency like that. Like so, two different wavelengths can be added or subtracted in that. Right. So this particular one is called a super continuum laser. Right. It's very compact, and the beauty of it is that like you can tune the wavelength of light. For example, in this case, we can vary from 400 nanometer, or rather in this particular laser, we can vary from 500 nanometer to 850 nanometer. And by adding up going to a different module, like we can go up to 2000 nanometer in wavelength. For example, the spot here, which you see, okay, this is a red laser light, which you are seeing. So this is right now, we put the emission wavelength at 600 and around 35 nanometers, 637.5 nanometers. Now if I vary this, for example, I can go to 550 nanometers. Okay, see that color? The color is like orangish now. Okay, so you can continuously change the color at will. So whichever color we want. Okay. So here we can also choose the bandwidth. What is the spectral width of it? For example, if I choose close to 0, you see like the color becomes more orangish. Right? So if I increase the bandwidth, for example, earlier case, we are using 75 nanometer bandwidth. So that's shown here. It's showing from 550 to 625 nanometers, right? That is 75 nanometer bandwidth. So it has orange as well as red colors mixed in it. So accordingly, the color will change. Right? So here we can set the bandwidth to 0, and then we can vary to 500. You see the green color. The color is green output now. Okay? And the red wavelength is I've already shown you. So I'll change it to deep red. Right? Now I'm going to infrared, near infrared wavelengths, for example, 800 nanometer. Right? You can see the color changing. So this is a super continuum source, and this can also be varied. The pulse width in time as well as the bandwidth can be changed. So it is a very versatile light source which we can use for different applications. Okay. Right. So this is a transmission reflection setup. Then I'll show you, yeah, I said I'll talk to you about this blue color one. So the blue color one in which the sample is mounted. Okay. So this has a long arm here, okay, and this has two ports. So one is used to uh, pump it down, evacuate it, right? So this whole thing goes to 10 power minus 6 millibar pressure. So, I mean, there is no air molecules inside that, or it's evacuated to as low air molecules as possible. Then we close this valve and insert a transfer tube through which will pump liquid helium into it. So the liquid helium is at 4 Kelvin temperature. So you can actually cool your sample down to 4 Kelvin, and then you can use heaters to vary the temperature of the sample from 4 Kelvin, which is minus 269 degrees centigrade, to up to room temperature, which is 30 degrees centigrade. Right? You can actually vary it up to 200 degrees or 400 degrees centigrade. Minus 270, you can go up to 400 degrees, plus 400 degrees centigrade by heating the sample. So by studying as a function of temperature, you can study like what is happening, like at what temperature the properties are, I mean, how the sample is behaving at different temperatures, what will be its properties. Okay.
High-tech lab.
So this is another setup. So in which we measure, for example, single photons, right? So the sample is mounted below this. So that spectrometer, it will be brought here and kept, and there is a lens here, right? So the laser light comes through this, right? And then it goes in, focuses, and then the reflected light is collected, comes through this beam splitter and then sent through this mirror to this pinhole. This mirror sends it here, and then it goes to the spectrometer. So this is another spectrometer with a
Excuse me, sir. Sir, please unmute your mics. There are some issues. Voice is not there. Excuse me, Dr. Gopal. Please unmute your mic.
Oh. Sir, you need to unmute yourself. Yes.
Yes, because the host has muted me and they didn't give me
There is
permission to
a
unmute
sound
myself.
disturbance,
Okay.
so that's why.
Yes.
Never-
Yeah. Okay. So I'm not sure when I was muted, but in any case, like so, I was talking about this here. Like we can measure in this setup, we can measure samples which are of micrometer size, right? So even in a single sample, we can measure it with the 1 micrometer resolution. 1 micrometer spots of sample can be probed. So why do we need it? Like for example, in quantum dots, right? So these are a few nanometer of size, right? And then we can locally change how the medium around it is, and then we can use it for different applications like single photon emission or single photon logic gates or things. So we look at like how the quantum dot behaves, right, by actually probing a single quantum dot at a time. Okay. So here the beam, the signal which is reflected beam is collected, right? Either the reflection or the emitted light in the reflection geometry. Whatever is emitted backwards is collected and then sent through the spectrometer. So this CCT is a high resolution one, which gives, which can detect few photons of light which is falling on it. So it's very sensitive detector. So how do we know whether we have a single photon or many photons? Okay, one way to check that out one way to check whether we have a single photon or many photons is something by using a beam splitter, which is a 50-50 beam splitter. Okay? Which means when light is incident on it, 50% is reflected, 50% is transmitted. Okay? So if you have only one single photon, right, can you split one photon into two? No, you cannot. So one photon is like a particle, right? So it can either get reflected in this path or it can get reflected in this path. Okay? So this is first path, this is second path. Okay. So if you measure what is the probability, so this is detector 1 and this is my detector 2. What is the probability that we are measuring a photon simultaneously in both the detectors? So both the detectors are detecting a photon at the same time. Okay. So as a function of time, if we measure the probability, so what we see is we see a plot like this. So at t is equal to 0, which means the length traveled by the photon along this path and the length traveled in this path L2, L1 is equal to L2, in which case a photon, if there is a single photon, it can either go to this or it can go to this. So the probability of detecting in D1 and D2 at the same time will be 0. So at t equal to 0, so the photon can go to either D1 or it can go to D2, detector 2. So the probability of finding a photon in both the detectors will be 0. So that will tell us if we have a single photon or more than one photon. Okay. So that's what we do. This is called a Hanbury-Brown-Twiss setup. So that's what we have in this black box here. Okay. And we use the avalanche photodiodes, which will, even single photon will trigger a huge amount of signal out of it. Okay. A pulse of electrical signal comes out of it. Okay. So I mentioned about time resolve measurements. In time resolve measurements, the main point is, so this is one laser path which is coming here. Okay. So the laser is coming from that side. Okay. Laser is coming from that side because my laser is there. So it's coming through this, and then it comes like this, comes here, and this is something called a beam splitter. Okay. Beam splitter is splits the beam, some part reflected, some part is transmitted. Okay. So the transmitted beam goes through this and then gets reflected through this mirror and then comes here. And the reflected beam from the beam splitter, so it's coming like this, it gets reflected, goes through the two mirrors there. So to the first mirror there, right side of my hand, and then goes to the second mirror there, and then comes back like this. Okay. So both the reflected and transmitted beams are coming back to this mirror here. But the main point is the reflected beam, which is traveling this path, is mounted on some black thing here. Okay. So that silvery thing which you can see here. Okay. So for example, that one. So that's a delay stage. So you can actually move it with 0.5 nanometer precision. Right? You can move it in 0.5 nanometer like that. Sorry, 0.5 micron, right? 0.5 micrometer precision. So you can see that you can set the time difference or the path length difference between the reflected path and the transmitted path. So the photons which are coming here, say you have 5 million photons or 1 million photons. So 500,000 go in that direction, 500,000 go in this direction. Okay. So, and then they're coming back. But then because the path length is slightly different and we can vary it, so we are setting the time difference between the reflected photons and the transmitted photons which are coming from this mirror onto the sample which is mounted here. Okay. So now you can do the measurement. So for example, there is a photodiode here. You can measure the transmitted light or you can measure the reflected light in this photodiode which is here. Okay. So now we can measure reflection and transmission simultaneously. Now if you have two beams, right? So the reflected one and transmitted one. So instead of having 500,000, you have 1 million photons here. So you send like 1 lakh photons there and 9 lakh photons in this path. Okay. So one is much stronger than the other one. So the stronger beam is called the pump beam and the weaker beam is called the probe beam. Okay. So when the pump beam comes first, so the probe beam comes little later. We delayed by changing the length of that path. Okay. And then we see what is the response of the sample. Okay. So after the pump pulse, say you come your probe pulse comes at say 15 femtoseconds later, right? 100 femtosecond later, 500 femtosecond later. Then you can see how you're able to how the sample is behaving at different times after the pump beam is coming. Okay. I also showed you like how the carriers decay down. You are exciting it to an excited state, and the carriers are, the electrons are decaying down to the ground state. So what we are trying to measure is how these electrons are decaying from the pump has excited large number of electrons into the excited state, and by delaying the probe pulses with respect to the pump, we are measuring how many carriers are still in the excited state. Right? So that's one way of, one measurement which we can do. Right? So we can do time resolve measurements using a simple thing. So the most crucial step is to use a beam splitter and a so-called delay stage where we can vary the path length, right, between the transmitted and the reflected paths. So we also use another tool to improve the signal to noise. So we use something like this. So this is a chopper. This is a mechanical chopper, a wheel which can be turned at very high speeds. If you see here, there are inner and outer slots. So they are not the same. right? So inner and outer slots are different. So you can put a beam coming through this, and you can modulate it. Like, so you're making it on, off like that. So you're making a pulses or some reference frequency at which you're chopping your light beam. Okay? So that reference can be given to a lock-in amplifier. So a lock-in amplifier locks to that reference frequency and measures the signals coming only at that particular frequency. Right? So I have a lot of light in the room. When actually we do the measurement, we switch off all the lights, and only light or the noise which comes out is because of the scattered light which is coming from the laser. Laser gets scattered at some points, and those scattered light also gives noise. So I want to reduce all that. So I modulate my light which is falling on the sample at a particular frequency at which this wheel is turning. Okay? And that reference frequency I use, I know that like my signal is coming only at the frequency at which the light is incident on the sample. So I measure using a lock-in amplifier. I measure the signal at that particular frequency to reduce the noise. So this is, to do what I tried to show you is a simple setup where we can do reflection transmission spectral measurements. I showed you a little higher end setup where we can do 1 micrometer spatial resolved measurements. Emission can be collected from 1 micron spatial spots, okay, with very low intensity lights. Right? Then I briefly described how we can establish whether we have single photons or not. Okay? And I showed you some basics of like how we do time resolved measurements. Okay, so you see these beam splitters. So if you see this one, this is very, very thin, right? What you see as Thor lamps, right? So that's a beam splitter. You can put a glass piece. Okay, this is a quartz piece, for example. This can also be used because glass also reflects some 4 to 6% depending on the type of glass. Like so, that can also be used as a beam splitter. But what we use is, but it'll have certain thickness to it. So what happens is if a light beam falls on a thick glass piece, so from the front as well as back side, so the photons will get reflected. The light will get reflected from the front as well as from the back. Okay, so we have seen the Fabry-Perot fringes, right? I hope you have studied Fabry-Perot fringes and remember that. So when you have a thick glass surface, glass substrate or sample, so the back and front reflected light beams, they can interfere and cause fringes. Right? So that will be bad for my measurements. So what we use here is this is a 5 micrometer thick polymer film, which is used as a beam splitter. Right? Right. So in this, we have what is known as a near field scanning optical microscope. Right? So here the idea is that so far what I have shown around, so these are all far field measurements. Far field means light which is far from the sample surface. How far? It should be farther than the wavelength of or a few wavelengths of light. Okay, so if I'm using 800 nanometer red light, okay, near infrared light of 800 nanometer. So if I'm measuring, say 1 meter away from the sample, so it's called a far field measurement. Even if it is like 1 centimeter, 1 millimeter, it's all far field. But you can also measure what is happening if I have a sample on the sample surface, like much less than or comparable to the wavelength of light, right? What is the property of the sample? Okay. So this is called a near field. So the far field is you're measuring it far from the surface. Okay. And in the near, farther where the light is, the wavelength of light is much smaller than the distance at which you are measuring the light. But in this case, we can put our sample here and we can measure using these, there are some tips, fiber tips here. We can scan on the surface, say 10 nanometer above the surface or just above the surface, touching the surface, or 100 nanometer from the surface. So these are all sub-wavelength distances, right? So smaller than the wavelength of light. At distances smaller than the wavelength of light, we are measuring the light intensity and trying to find what are the properties. So the near field properties of the sample could be very, very different from what we see in the far field. So for some applications, for some studies, we need to do these near field measurements. So we do far field, we do near field measurements. So this is, for example, an avalanche photodiode. So what you study in basic electronics, an avalanche photodiode is like you bias your photodiode in reverse bias, and just at the knee where the breakdown happens, just before the breakdown happens. Okay, so when light falls and the light is absorbed, the photon is absorbed, an electron is excited, and that electron is good enough to trigger the avalanche. So even with few photons, you can generate a huge pulse of electrical signal from this avalanche photodiode. So you can use this to measure single photons of light which is falling on you. Okay. So this is another small spectrometer. As I said, like the bigger one has a higher resolution and the smaller one has slightly poorer resolution. Okay. So this is a near field spectrometer which we use. It's called near field scanning optical microscope. This is different from the normal microscope which we all see in daily life. So here we look at the transmitted reflected light. Okay, so mount the sample here, and then what we are measuring is far from the surface of the sample. There, using a fiber tip, we measure on the surface or at distances much smaller than the wavelength of light. Okay, so that's more or less the lab. So there are lots of pumps here. So this is a vacuum pump. As I said, the cryostat needs to be pumped to low temperatures. If we do not pump it, what happens is at 77 Kelvin, right, the nitrogen is going to liquefy. Right? So air has about 77% or about 70, more than 70% of nitrogen in it. So if we don't evacuate and we start putting liquid helium and then try to lower the sample temperature, what happens is like the air molecule starts becoming liquid. So that liquid droplets will form on the sample and all around the cryostat. So you don't want that. So you pump down the all the air out. So using this is a turbo pump. Yeah, this is like a aeroplane engine, right? So there is a very high speed rotating fins, so which will suck out the air from the cryostat region. Okay. So we use this to pump the cryostat first, then use the transfer tube to transfer liquid helium to the cryostat. Okay. So you can also do magnetic field measurements. So where, for example, see this is an electromagnet. Okay. So here by changing the voltage which is applied to the coils, we can get up to 1.2 Tesla of magnetic field. And then we put our sample here and using in the, so for example, you see here, there are two arms. Okay. There's one arm here and one arm here. So you can put light through one arm and then look at the reflected light, or you can send light from one side and look at the, either the reflected light or something, okay, or transmitted light. Okay. So you study Faraday effect, Kerr effect, so which requires magnetic field to apply on the sample. Right, so that's all I have. If you have any questions, I'll be happy to answer. So does anyone have a question? Hello.
हाँ जी बेटा कुछ और क्वेश्चंस पूछने हैं आपने सर ये इस लैब का नाम क्या है जो आपने अभी दिखाई
This
है
is the Photon lab. In my last slide yesterday, it was there like FOTON. We study fundamental optics.
सर ऐसे इसमें हर फील्ड की लैब्स हैं TIFR में जैसे न्यूक्लियर फिजिक्स की भी होंगी और बाकी कंडेंस्ड मैटर फिजिक्स की भी होंगी
So I don't want to, I mean, I can show the terahertz part and also clean room, but I don't want to.
scientists might be working at this time I think it's a working time for them
Okay. If you are muted, so please send. Okay, how many types of photon detectors do we have in the lab? How many types? So we have photomultiplier tubes, we have photodiodes, we have CCDs. Okay. So at least 3 types, and we have pyro detectors. Okay. Like for example, a pyro detector will look something like this. Okay. And photodiodes have shown. Example, this one, this is a pyrometer. So light incident on it, so there is no semiconductor piece like in a photodiode. So the light falls on this, and the change in the heat is measured by the pyrometer. Okay. This is used for high power laser intensities, and for lower powers we can use photodiodes. Okay, something like this. So the shiny thing which you see, so that's a silicon chip which is used as a photodiode. Okay, and I showed you the avalanche photodiode, which is basically a photodiode which is reverse bias. So this is an avalanche photodiode which is cooled. So this entire thing is to cool it down, cool the photodiode to lower temperatures so that the thermal noise will be very weak. So what factors we should take care of while doing the experiment? So it depends on the experiment which we do. So for example, when we do the optical measurements, for me, all this room light is waste. So typically the kind of atmosphere we work in, so everything is off, all lights are off. Okay. So when we measure the number of photons, the dark photons which are coming in the lab. So they're typically of the order of 10 photons or less. Okay? If you see all our windows and everything, so we switch off it, we have darkened windows. Okay? So then to further improve the noise, I said like we do the locking detection. Right? So that like we modulate the input light and then we measure the signal coming only at the particular frequency where we are modulating the input light. Okay. So sources of noise will be from noise in the uh, light source, right? So that we can't do much about, but the external noises are what we take care of. Fluctuation in the temperature of the sample. So we use cryostat to maintain the temperature. So other thing, when I said, when I showed you this beam splitter, this is 5-micron thin film. See, if you have an air-conditioned room, the air currents will vibrate that 5-micron film. So that also causes disturbance in your signal which you'll be getting. Okay, so you need to take care of these things so that like your air currents are uniform in your lab and inside.
Any other
Any
questions,
other questions?
students?
Typically when we have a open day or science day, so we show something like this. Like so, use this. We can measure the diameter of hair, thickness of hair, by varying the. For example, I showed this laser super continuum source. So we put a hair here, and then we measure the diffraction pattern which is coming out. You all studied diffraction, right? So when the light falls on this and the thickness of my finger is very small, so then how bright is the single photon diode when, okay, you can't see the photons at all, right? So if you the whatever I can see, right, will be at least like tens of thousands of photons. So we're talking about one photon, we cannot see that with our eye. Yeah. So what I'm saying, like so if my hair is very thin, so then the light beam which falls on it, so it gets diffracted in the vertical direction. If I put it this way, the diffracted spots will be in the vertical plane, 1, 2, 3, 4, 5, 6. So different diffraction orders. By measuring the separation between them, I can measure using this formula. So I can measure the thickness of hair. So the one which we typically measure is of the order of like so 50 micron or so. Okay? So if I put my hair this way, if it is this way, my diffraction orders will come this way. But if I put my hair this way, so the diffraction orders will be along this direction, for example. You see here these spots. So each one corresponds to different order, right? So we can measure the separation between them. If I change the color, if I change the lambda here, then the separation changes. So you can easily see in this, like so, how the shift in the diffraction pattern is by varying the power, varying the wavelength of light. Right? Any other questions?
Any other query?
First, you can write the chat box if there is any other query.
From yesterday's talk or today's, like so, whatever you have seen so far?
Okay, so no other questions?
If you have a question but don't want to ask now, you may ask me later on. Okay,
Yes,
somebody
Sabir,
asked, do we have
you
electron
continue.
accelerator in the lab? Yes, so the electron accelerator in TIFR, we have a pelletron accelerator, which is a 14 MeV, 14 mega electron volt accelerator, and also a linear accelerator, which is there. So, but not in our lab. So what we use as far as accelerator for electrons is concerned, we use a SEM, a scanning electron microscope, and a transmission electron microscope. So they are inside the clean room, right? So they're like, yes, electrons are accelerated to the one which we use. The SEM has about 30 keV, kilo electron volt.
So I guess there are no more questions from our students, and students will ask, definitely will be asking later on when they feel like. So thank you very much, sir, for letting us in your lab. It was a wonderful experience for all of us, sir. We have witnessed so many sophisticated instruments under one roof. Students learned about continuous and pulse laser. We witnessed titanium sapphire laser, helium cadmium lasers, helium neon lasers, different types of spectrometers, learned about the various measurement techniques. We also learned about the functions of vacuum pumps and all. So it was a wonderful experience altogether, sir. Thank you very much for
Thank you,
sparing
ma'am.
that much of time for us, sir.
Thank you,
For
ma'am.
students, I want to tell you that in the chat box, I'm sharing a feedback form with you. Please fill this feedback form and submit it. In the chat box, I guess all you can see is our link which is provided to you. Just click on that, and this will be taken as your attendance too. Now for vote of thanks, I would like to request Parminder ma'am to please present a token of thanks to Dr. Venugopal, sir.
Dear Dr. Venugopal, it has been indeed a treat for us and our students to visit such a renowned and prestigious lab. Our students are really lucky to have such an exposure at this age. We got this exposure now only after so many years. Dr. Venugopal, I, on behalf of Kanya Mahavidyalaya Jalandhar, and especially our whole physics department, would like to thank you from core of my heart for giving us your precious time. We are all honored, sir, and we will look
Thank you,
forward
ma'am.
to many more interactions of this type. Thank you so much once again.
Thank you, ma'am.
Thank you, sir.
So could I log out?
Yes, sir. Thank you so much.
Thank you.
Anything may end the meeting.
Thus, hope to meet you the next
Hopefully.
event.
Hopefully,
Yes.
we will meet
Yes.
the person.
Yes, ma'am.
Yes.
And thanks to all the
Bye.
participants. Yes, sir.
Thank you.
Thank you.
Thank you. Bye.
Bye bye, sir.